Good morning, everyone. Today we have Felipe Rincón from University to tell us about tropical ideals.
Great. Thank you so much for the invitation to speak. My plan is to tell you about these objects, tropical ideals, which are objects I've been thinking about for several years now. And I'm going to try to make my exposition very matroidal. So these are very matroidal objects, and I'm going to try to distill the matroid theory behind these things. My plan is to go slowly. I only have 13 slides, so please let me know if anything is not clear. I'm not going to assume that all of you are familiar with tropical geometry, so I have one cartoon slide about what tropical geometry tries to do. And for the purposes of this talk, we can think about it as tropical geometry is just some tool that takes algebraic varieties, algebraic subvarieties of affine space. So you take an embedded algebraic variety and you do some process to it, you tropicalize it, and you turn it into a polyhedral complex. Okay, something that looks, like that. So combinatorially defined polyhedral complex. And the idea is that this process retains some information about algebraic varieties, and that's why it's useful and why it has been successful in many things. So for instance, if you want to count severity degrees, so like the number of cubic curves in the plane that go through 8 generic points and have one nodal singularity, one self-intersection, then, well, there's a finite number of those, and it turns out that the answer is 12 in the classical, for classical curves. But if you try to count the same thing tropically, like number of tropical curves going through 8 points, 8 generic points, having one self-intersection of degree 3, you get the same answer, all right? So tropical geometry is very good at solving enumerative problems in the sense that you get the same answer tropically. So this is why a lot of people are interested in this process of tropicalization, let's say, turning algebraic varieties into polyhedral complexes. And let me say a bit more about how that process goes, because we're going to need this later. So let's say you have an algebraic subvariety of affine space. And let's say it's given as the zero locus of some ideal of polynomials on n variables with coefficients in a field K. So if you have a polynomial f, just some coefficients times some monomials, and I'm going to use this, x to the u, the u is a lattice point, so it indexes all the exponents of the variables. I'm going to talk about the support of the polynomial as the actual monomials or the exponent vectors that appear in the polynomial. So the coefficient is now 0. And then I'm going to be interested in the collection of all supports of the polynomials in the ideal. So this is what I'm going to call the tropicalization of the ideal J. Just collect all the possible supports of all the polynomials that appear in your ideal. So this is now like a collection, an infinite collection of subsets of lattice points. Each of these is a finite subset of lattice points, and then I'm collecting all of them for all the polynomials in the. So what's the tropicalization of your algebraic variety? What you do is you take all these collections of supports and you impose the condition that you impose the condition that you look at all the common tropical zeros of these subsets. And what does it mean to be a tropical zero? It means that you look at all the directions, the vectors A in Rn, such that for each of these subsets, when you consider the dot product between your direction and all the lattice points in the subset, the maximum dot product is attained at least twice. Okay? So this is the max attained twice condition that maybe you guys have seen in tropical geometry, or the mean attained twice. I'm going to use the max convention here. But to draw a picture, so if your subset S is a collection, is the support of some polynomials, so it's just some monomials that appear in your polynomial, then the zero set, tropical zero set for this S, what I'm calling the set of A's for which the maximum is attained twice, would be you look at all directions in the plane where the maximum dot product with these 5 points is attained twice. So for instance, not a direction looking like upwards, because then the maximum would only be attained twice by this monomial, but you really want, like, let's say the origin is here, I don't know. These directions, because there the maximum is attained by these 2, or these directions perpendicular to this edge, or these directions perpendicular to this edge, or those directions perpendicular. It's really, but another way of saying that is that it's the codimension one skeleton of the normal fun of the convex hull of S. Yeah, so this is what I'm saying here. It's the codimension one skeleton of the dual normal fun to the convex hull of the elements of S, and then that's the condition for that subset S, and then just take the intersection of all those codimension one skeleton for all the S appearing in your infinite connection. Does that make sense? So it's some kind of combinatorially defined subset of Rn. That's the tropicalization of the variety.
Now, is there any kind of behavior under coordinate changes, or is it just behave in an unpredictable way?
So
Like if you chose a different basis besides the basis, like y.
it is very sensitive to how the variety is embedded there, and it behaves nicely under monomial changes of coordinates, but not under linear changes of coordinates. That might change the whole structure of the file.
But it's not random.
It's not random, no, of course, it's determined, but it's it changes the combinatorics of what you get in the end. Yeah. Just to be completely clear, and so that you have an example to think, or just to be completely clear about what we mean, just let's tropicalize a line in the plane. That's the simplest thing we could do. So, for instance, let's take the ideal defined by this linear polynomial in two variables, x plus y plus 1. So I'm going to think of it as living in the polynomial ring K is just your favorite field in two variables x and y. So as an ideal, the classical ideal that defines the line is, well, the generator, but also all the multiples of the generator, right? So for instance, x times the generator, y times the generator. You have things that are, like for example, this one minus that one, and then you get this one here, and of course, all multiples. Then the thing that I'm calling the tropicalization of the ideal is looking at the supports of all these polynomials. For instance, this one has support. And instead of writing the lattice point corresponding, so this would be like the lattice point 1, 0, 0, but I'm just going to, no, 1, 0, I'm just going to write x. I'm going to identify lattice points with monomials, so x, y, and the origin, which is the monomial 1. This one has support x squared, x, y, x. This one has support this one has support that. So you get all the infinite collection of supports. And then for each of these subsets, you require the condition that the minimum dot product with these ones is attained twice. With these ones is attained twice. So yeah, so for instance, this set here looks like a triangle, right? Origin, x and y. And then you look at the codimension one skeleton of that, of the normal fun of that, which is these three directions. And if you think about it, because all of these were multiples of this one, then that means that all these Newton polytopes are going to have this one as a summand. So they are also going to have these three directions at some point. And that means that these don't impose any new conditions on your tropical variety. So yeah, so the set of directions where the minimum is attained, the maximum is attained twice for all these subsets, it's exactly these red directions that I drew over there. And that's the tropicalization today. Yeah, does that make sense? Is that example? I'm going to focus later on this, and we're going to forget a little bit about the varieties, and we're going to focus on this collection of subsets. But do let me know if something is not clear. I guess the way it's not obvious that this is even a polyhedral fun, right? But that is true. If you start with an algebraic variety, then when you tropicalize by doing this procedure, you get a finite polyhedral fun. And in principle, you have infinitely many conditions here, infinitely many polyhedral conditions, but it turns out that, you can make them finite, only finitely many of them matter in the end. So you get a finite polyhedral fun that remembers information about the algebraic variety, like dimension, for instance. The fact that we're tropicalizing a curve in the plane means that the polyhedral fun we get here is one-dimensional, or it also remembers the degree of the variety, for instance. But also an important fact is that you cannot get any fun as a result of this process. You get something that is called the balance fun. And in matrix theory, I guess we like those. So the maximal cones here come with some weights, with some multiplicities. In this case, it's 1, 1, and 1. And they satisfy this like zero tension condition that if you pull with those weights along these lines, you get the point in the middle is balanced. So you get a balanced point. Good. That's the background I want to give you on tropical geometry, and then let's try to talk about tropical ideas. So how did I start thinking about tropical ideals? Well, it turns out there's this paper in 2013 by Jeff and Noah Giansiracusa, they're brothers. And they wrote this paper saying basically, okay, we're focusing on these tropical varieties, but maybe we should be remembering more than just the variety. Maybe we should be remembering some algebraic information as well. Right? Just like we in algebraic geometry, we like talking about schemes and not only varieties these days, then we should try to think about what a tropical scheme is. And for that, we need some algebraic information. And they define some, what an affine scheme, tropical scheme should be in terms of some congruence on the semi-ring of tropical polynomials associated to a variety and so on. Later, with Diane McLagan in this paper in 2014, we realized, okay, this congruence that they're defining is actually just equivalent to the information that I just described to you, the tropicalization of the collection of supports called polynomials. Okay. So this is like the algebraic information, the tropical scheme that we want to remember. And then in 2016, we proposed the following. Okay, so let's try to study these collections of supports that arise from polynomials in an ideal. And well, there are some properties that these collections satisfy, right? Not any collection of subsets of lattice points can arise as this trop J for an ideal J. So there are some properties that they satisfy. And I like doing some audience participation in my talk. So I'm going to ask you guys to come up with properties that you think this trop J satisfy. I'm going to start with the first one, which is the empty set is always there. And that's because the zero polynomial is in your ideal. So the support of the zero polynomial is set kind of by convention. So this collection is going to have the empty subset there. Can you guys tell me other properties that these infinite collections of lattice points, of subsets of lattice points satisfy?
You have something you can multiply by a variable.
That's exactly right. Yeah, that's the next one. If you have a subset of a collection of lattice points that is the support of a polynomial in your ideal, then you can, well, the polynomial you can multiply by a variable, and that's going to have support. Just translate the support upwards or rightwards. Or, yeah. So for every variable, you can shift your subsets to the upwards or to the right, and you should still get something in your ideal. Any other properties that these collections should satisfy?
Minkowski sums, maybe?
Minkowski sums, it's going to be a consequence of this one and the following, which is that it's closed under unions. At least if your field is infinite, then whenever you take two polynomials in your ideal, if you take like a generic linear combination of the two, then nothing cancels out. And then you get a polynomial where the support is the union. Right.
There should be also some elimination. If you have something and another thing that when they share one, there should be something contained in the union minus that one.
That's exactly right. Yeah, I love giving talk to this. And exactly in the same order. And yeah. So yeah, exactly what you said. If you take two supports that appear in your collection, that means there's two polynomials, one with this support and this other support. And let's say they share some common monomial. Well, you can from the two polynomials that give rise to these supports, you can like take a linear combination that eliminates that monomial that they have in common, right? And what that's going to give you is a polynomial with some support is 3 that it only uses the monomials that appeared in one of the two. It doesn't use the one that you eliminated. But if a monomial appeared in only one of the two, then it has to appear in this elimination. So it contains S3 contains the symmetric difference of S1 and S2 and is contained in the union. Good. And yeah, and what we did in this paper is, well, let's propose this as a definition. Let's think about the collections of finite subsets of lattice points that satisfy these 4 axes. And this is what we're going to call a tropical ideal. This is a tropical ideal, purely combinatorial object, collections of lattice points satisfying these 4 axes, right? If it turns out that your collection of lattice points actually arises from an ideal with coefficients in a field as the supports of that, then we should think of those as the realizable ones, the ones that come from an honest field, but there are non-realizable examples. And let me make some comments on these definitions. So the way I'm presenting it here is kind of, it's a little bit arbitrary. Why stop with these axioms? But for instance, from the tropical point of view, this is a very natural concept. It's just saying it's. I'm not going to explain too much on this, but it's this. Another way of saying this is that it's an ideal in the semi-ring of tropical polynomials where, truncated degrees are a linear space, a tropical linear space. This is encoding the tropical linear space, and tropical linear spaces in tropical geometry are very natural, and this is the analog of linear spaces. So we do like this definition.
So that's true even without assuming any like homogeneous.
That's right. Yeah. So I'm trying to do the non-homogeneous case here, and what I'm saying is true in that case. Let me tell you another way of thinking about these tropical ideals. Okay, so let's denote by delta D the collection of all monomials. I just rewrote the definition here. This is just the 4 axioms we had discussed. So let's call delta D the all monomials of degree at most D, and then let's truncate our collection of subsets to just those that live inside, those that use subsets of degree at most D. It turns out that these axioms here, in fact, 0, 2, and 3, are basically saying that this collection is the set of cycles, so unions of circuits of a matrix. If you go to one of these red books, white books on matrix theory, and you look how do you axiomatize matrix by unions of circuits, by cycles, you'll see exactly these 3 axioms. The empty set is a cycle. If you take 2 cycles, the union is a cycle. And if you have 2 cycles, then they have some elimination property. This is like the circuit elimination property, but for unions of circuits and not just for one circuit. So 0, 2, and 3 are saying you have a matrix. Whenever you truncate your ideal to some degree, you get a matrix. But of course, so these matrices keep growing on the degree. So maybe the way I really think about tropical ideals is like this. It's like an infinite tower of compatible matrices. And what do I mean by that? Well, it's like an infinite sequence of matrices, MD, 1 for each degree. And the matrix MD is the one that tells you what the polynomials of, or the support, the final subsets of degree D are at most D. So MD should be a matrix on the ground set delta D. Well, delta D is monomials of degree at most D. So the ground sets are kind of increasing every time with D. But then they need to be compatible in the sense that they need to satisfy this TI1, that there's some compatibility between the polynomials of degree D and the polynomials of degree D plus 1, in the sense that, well, if you have a circuit in degree D, a polynomial in degree D, and you multiply it by a variable, you should get a circuit in degree D plus 1. And that is really just just saying that you have a quotient, a matrix quotient between the matrix of degree D. When you take this matrix and multiply it by xi, like the circuits here, you multiply it by a variable, you should get circuits or unions of circuits in the one in degree D plus 1. So this is the matrix in degree D plus 1, restricted to only the monomials that are divisible by xi. And this thing here is equivalent to that. So this is really the way I think about tropical ideals. It's like a sequence of matrices where the ground sets are monomials of degree D, and they get bigger and bigger, and they need to be compatible, like quotient-wise. You take degree D, and no matter how you shift it to the next degree, you should get a quotient of that. Okay.
Is there anything about finite generation of the ideal? Like, how do you know that there aren't things that get added forever and ever?
Yeah, that's a great question. And these things are not finitely generated. So in the sense, so what do I mean by finitely generated? Generated as, if you fix a finite collection of subsets and you take all like unions of them, and you won't be able to find just finitely many subsets that generate the whole ideal. Because of this elimination axiom, there needs to be some way of eliminating. And I'll say more about this later, a lot more, but I don't know a way of like finitely describing these things. And this is one of the big things I would like to know. I'll say more about it. But yeah, these things are not finitely generated, which is tricky. I should also say that it's fine to replace quotient by just like, it's an isomorphism of matrix here. So the circuits that you see in degree D, when you multiply them by a variable, you should get a circuit in degree D plus 1. That just means you're restricting to ideals that are like saturated with respect to the product of the variables. That if you see a polynomial in degree D that is a multiple of, where all the monomials are multiples of some variable, then you already see it in degree D minus 1. Those are already very interesting ideals. They define like subschemes of the torus instead of subschemes of open space. It's fine if you restrict to those, and those, yeah. So you could say here that this is an isomorphism, not just a quotient. And just to get a very interesting notion. Good. Are we happy with this definition? So here, let me give you some examples and talk about the realizability of these things. So the first example is a very simple example, just to make sure we're all on the same page. So for instance, with one variable, take the collection of all subsets. So the monomials are just like 1, x, x squared, x cubed, and so on. Lattice points in one dimension and in one line. And then our collection of subsets is going to be finite subsets that have at least 2 elements. Subsets with at least 2 elements, or 3 elements, 4 elements. That I claim is a tropical ideal. If you think about it as a sequence of matrix, like the matrix, what that tells you what the polynomials are in degree d plus 1, and so on, I'm just putting the uniform matrix 2d on each. Yeah, so the rank, no, 1d. So the circuits are anything that has 2 elements, and the unions of circuits are anything that has at least 2 elements. So I'm just putting matrix 1 and 1d as these matrices. Do you guys, can you see if this is realizable or not? Is there a classical ideal in one variable where the supports of the polynomials in the ideal are exactly all the subsets that have at least 2 elements? I claim it is realizable. This is just something to check. This is what you would get if you look at the ideal generated by just one simple binomial, x minus 1. Yeah, so if you think about what are the supports of polynomials in this ideal x minus 1, well, you have x minus 1, you have x squared minus 1, x cubed minus 1, you have all binomials, and then by combining those binomials, you can get any subset that has at least 2 elements, right? So the supports of the polynomials appearing here are exactly the subsets that have at least 2 elements, and that's why this one is realized. It's just a tropicalization of that. But pretty soon after we started thinking about this, we realized, okay, actually, yeah, they are not all realizable. And here's an example I like a lot of a non-realizable ideal. So let me spend some time telling you about this. This is a tropical ideal in 2 variables. So I'm going to be defining to use subsets of lattice points in the plane. And it consists of the collections of, so I'm going to tell you the circuits of these matrices. The circuits are subsets C that consist of k plus 2 monomials inside a triangle of size k. Standard triangle of size k. So when I say a standard triangle, I mean a triangle that is like vertical, horizontal, and slope minus 1. A triangle that looks like this or like this. This is a triangle of size 1, triangle of size 2, so on. And for instance, if you have 3 monomials inside a triangle of size 1, like these 3, 1, x, and y, that's going to be a circuit that classifies as a circuit of one. Or here's another example of 3 monomials inside a triangle of size 1. These 3 monomials, y, x, y, and y squared. There are 3 inside a triangle of size 1. So that I'm going to put as a circuit of my matrix in degree 2. Here are 4 monomials inside a triangle of size 2. So k plus 2 monomials inside a triangle of size k. That's a circuit. Or here's another example of a circuit, but this one is now in degree 3. These are 5 monomials inside a triangle of degree 3. So this is another example of something I want to put in my collection, and so on. Yeah, and then I'm saying take finite unions because these are just the circuits. So unions of circuits are just unions of these things. And actually, technically, I need to focus just on C's that are minimal with this property. Like
Even k is minimal with respect to this property. You're taking the smallest k that the circuit sits in.
so, for instance, I'm classifying. I do want to look at triangles like this one. They don't have to start here at 1, but
But I mean, it's in a bigger triangle, but the k is the minimal. Like that's the k.
That's right. Yeah. I want to look at. Yeah, exactly. The k is the minimal. If you take some collection that satisfies this, but it turns out some sub collection lived in a smaller triangle already satisfying this collection, then you don't want to consider that. Just the minimal ones. Yeah, they're meant to be circuits, so they're minimal with this property. Actually, I learned about this matrix from a paper of Federico and Sarah Billy on black arrangements of subspaces, something like this. And they run into these matrices because these are the matrices that describe, I don't know, I forget exactly what, like which collections of subsets intersect or which don't. And but they never consider all of them at the same time. Like for them, they fix one n and then they get one of these matrices, like the one on this. But it turns out that if you put them all together, like a sequence of matrices, they form a tropical ideal, which is quite interesting.
So sorry, so the third one is a cycle but not a circuit, or?
No, this one is a circuit.
So the third one.
This should be a circuit as well. So it's 4 monomials inside a triangle of size 2, but no proper connections inside that.
That one, yes.
So if you erase that one, you still, these are spread out.
I confused 3 and 4, sorry.
I see, yeah, okay. So the claim is that these are a tropical ideal. They are circuits of a matrix, and you can check that it's not that hard. So they satisfy this elimination property.
And the second one, you have 3.
These are 3 inside a triangle of size 1.
Okay.
So the triangle I look at here is just this small one. Yeah. So they classify. So for instance, this is why these matrices are compatible. If you have something in degree 1 that is a circuit and you shift it upwards, still you get something in degree 2. That's why they satisfy this compatibility condition. And so they form a tropical ideal. But I claim that the tropical ideal is not realized. You cannot find an ideal with coefficients in a field where these are the supports of the polynomials in the ideal, and that's quite easy to see, actually. I can give you the proof in one line, pretty much. Suppose it was the tropicalization of a classical ideal, J with coefficients in a field, K. Well, because you have this subset here, 1xy, that means that there needs to be a polynomial in your ideal that uses these 3 monomials, so something times x plus something times y plus some constant. You can scale your polynomial so that this is a 1. Then you can scale the variables, change x for a scaling of x, change y for a scaling of y, so that these coefficients are 1. Just to simplify what I'm going to say next. So you can assume that, without loss of generality, that this linear polynomial is in your ideal, J. But then take that polynomial and multiply it by this kind of carefully selected quadratic polynomial where there's a lot of cancellation. And so if you multiply it by this one, this should also be in your ideal. But then when you expand this out, you just get x cubed plus y cubed. So this one plus this one minus 3xy, which depending on whether your characteristic is 3 or not, might actually be there or not, plus 1. But in any case, these are like 3 or 4 subsets. This one, that one, that one, for lattice points that are not that are spread out, that are not k plus 2 inside a triangle of size k. So yeah, so this should be your ideal J, but this is not one of the things you put in your tropical ideal. This one is not. It's 4 monomials inside triangle of size 3, not 2. Yeah, so these things behave quite interesting. Like all these matrices are actually transversal matrices. They're realizable matrices, but somehow what makes this a non-realizable ideal is that they don't fit together one on top of the other. Each of them is realizable, but the realization do not agree to form an ideal.
If the tropical ideal is realizable, does it imply that
Sorry, say again?
if the tropical ideal is realizable, does it imply that the matrix are?
Yes, yeah. So if the tropical ideal is realizable, then in degree, the matrix you put on degree D is like the tropicalization of the linear space of polynomials of degree D in your ideal, which is going to be so yes. You get like a realization already from the ideal. Yes.
So the realizability is about the compatibility of these matroids? Or
Yeah, I mean, I guess what Basile is saying is that if you put a non-realizable matrix in some degree, then that doesn't have a chance to be realizable because the realizable ones have all realizable matrices. But it's much more than that. Like all the matrices, like these are all realizable matrices, but still they don't give you a realizable tropical ideal.
But then if you add some compatibility conditions, does that characterize the realizable tropical ideals?
I mean, I wouldn't know what condition makes it.
Compatibility means.
Like all these quotient maps, they say that all these quotient maps are realized as well.
But they need to be like realizable from an idea. Like the way you're embedding these things is like you don't want to think of this as a space, just any subspace, but like a space, a Veronese embedding of something that comes from degree 1, and this is like a Veronese of something that comes from degree 1. If you already have this one, so it's a bit tricky. I wouldn't know exactly how to phrase the realizability purely combinatorially, and my guess is that it's harder than phrasing the realizability for matroids, just for matrix. So I don't think there's much hope in trying to combinatorially characterize the realizable ones.
So, sorry, just a clarification. Before you showed this slide, there was a compatibility about the matrix.
That's right. Yeah.
What was that about? This is just a property of the consequence of the previous definition.
Yeah, this is just saying this is TI1, that if you have a circuit in degree I and degree D and you multiply it by a variable, you get a circuit in degree D plus 1. And this is like, yeah, this still doesn't certify realizability. Like these matrices here satisfy that. If you take a circuit in degree 1 and you multiply it by Y, you get a circuit in degree 2, but still this cannot be the collections of the one.
I see. Thank you.
One idea. Good. So in some sense, the definition, at least to me, is quite natural, and it's really very natural from the tropical point of view. And it involves matrix, which I really like matrix. But then the question is, how far can you go with this definition? Okay, how interesting is it to study these collections of subsets, these tropical ideals?
Is there like a homogeneous version of this example? Can I just homogenize everything?
That's right. If you homogenize, then you get so let me tell you some of the things I've been thinking about and things we have been able to prove and things we have no idea, and I would really welcome any help if any of you has any ideas about this. So for instance, one nice thing you can do with tropical ideals is you have a notion of Hilbert function, right? Because well, you have a sequence of matrices, and matrices have a well-defined notion of rank, of dimension. So immediately you get a notion of Hilbert function, which is, yeah, it's the function from natural numbers to natural numbers that to every degree D, it just gives you the rank of the matrix that you have in that degree. Yeah. So this agrees actually with the classical Hilbert function in the sense that if you start with a classical ideal and you tropicalize it, you look at the supports, then the Hilbert function defined combinatorially from the collection of supports is just the same as the Hilbert function that tells you what the dimension of these quotients, vector spaces are. Yeah. Okay, so this is, you think of it as a generalization of the Hilbert function for ideals. Now you can talk about Hilbert functions of non-realizable ideals. And what's quite interesting is that they still behave nicely in the sense that just this compatibility condition that tells you that the matrices are one a quotient of the next one implies already that the ranks cannot behave arbitrarily. The sequence of ranks eventually becomes a polynomial, which is what you would call the Hilbert polynomial of the tropical ideal. Even if it's not realizable, they have a Hilbert polynomial. So they have some dimension, for instance, which is the degree of this Hilbert polynomial. And now related to the finite generation thing, tropical ideals, as I said, are typically not finite generated. Like very few, maybe just the monomials, or if you have binomials, are finite generated. But as soon as you have a trinomial or something, this elimination axiom makes them not be finite generated. But still, because things like, yeah, they have a Hilbert function, you can prove that there are no infinite ascending chains. I guess if you fix the number of particles, so they still satisfy the ascending chain condition. Okay. Yeah. Each of these is not finally generated, but still we cannot create an infinite sequence of growing tropical ideals, one containing the next, which is good. We like having some kind of finite control on how chains of ideals. If we want to think of these as schemes, for instance.
The leading coefficient of the Hilbert polynomial is supposed to be the degree.
That's right. The leading coefficient is supposed to be the degree, and I don't think that has been written down, but it follows from things that, yeah, it's the degree in the sense that if you look at the variety, you intersect it with a subspace of the complementary dimension, that's the number of points you get. So it's given by So I have another slides of connections between varieties and between the geometry and the algebra. Of course, you can define the variety for these ideals in general, the non-realizable ones as well, just in the same way we did before. Just take the variety of a tropical ideal to be the directions that satisfy this max attained twice condition for all the subsets in your ideal. So this is, if you apply this to a realized tropical, to the tropicalization of a classical ideal, you get the tropical variety. Given the tropicalization of the variety, but you can apply this definition to non-realizable tropical ideals and still get some kind of subset of Rn. And what we proved in this paper is that actually, the compatibility condition on the degrees, the matroidal property, implies that this is a finite polyhedral complex, still finite polyhedral complex. The dimension of the polyhedral complex is really what you would expect from the algebra. It's the degree of the Hilbert polynomial of the ideal. So just how fast these ranks grow tells you what the dimension of the variety is. And then later it took us a while to come up with this balancing condition. The varieties of these tropical ideals, even if they are not realizable, have to be balanced balance in the sense that maximal cones come with a multiplicity and they satisfy the zero tension condition around every codimension one phase. Yeah.
Is the tropical ideal of the thing you mentioned, if you homogenize it, is it like the Bergman of U2-3?
That's right, of U2-3, yes, exactly. So it's the tropical line. And you can think of this as a non-realizable scheme structure that you can put on the line. The usual one we come up with is the realizable one, and this is a different one that's not realizable, but still the variety is just the line. Exactly.
How do you come up with the weights that the existing balance?
Yeah, by looking at Grobner degenerations of this. So if you want to know what the weight of a point here in the maximal cone is, what you would do is you would take your ideal and degenerate it according to a weight that sits in the interior there. You get some, so initial ideal, tropical ideals are well behaved with respect to Grobner degenerations. You can degenerate and still get a tropical ideal. And then if this is a maximal cone, you can prove that that degeneration is basically a product of like an Artinian ring with a free ring, and the dimension of this Artinian ring is what tells you what that multiplicity is. So just the same multiplicity that you would assign to a tropical variety, you can do it for tropical ideals. Yeah. Following the same recipe, pretty much. This is just, it's a generalization of what happens in the realizable case. You can extend it to non-realizable. Something we don't know how to do, for instance, is what does it mean to be irreducible? What does it mean to be prime, right? So find a useful, we've thought about this for a while, and some natural definitions don't really, either they're too restrictive or they don't imply things you would want prime to imply, but find some interesting condition on these matroids, on these subsets, that ensures that the variety, for instance, is a pure polyhedral complex, that it only has maximal cones of the same dimension. That's that we don't know. What should be the analog of irreducible in this context? All right. So the question then arises, okay, we know that the varieties of these tropical ideals are balanced polyhedral fans. And then I started wondering, okay, how general can these polyhedral fans be? The ones that arise as the variety of a tropical ideal. How can any polyhedral fan that is balanced arise as the variety of a tropical ideal? Well, there's a collection of balanced polyhedral fans that we like a lot, which are Bergman fans of matrix, right? So that naturally leads to this definition that I'm giving here. We're going to say that a matroid M on, let's say, a ground set of n elements is tropically realizable if it turns out you can find a tropical ideal on the same number of variables, x1 up to xn, such that the variety of that ideal is the Bergman fan of the matrix. Okay, so Bergman fans of the matrix are balanced polyhedral complexes. There's a chance that they can be varieties of tropical ideals. What are the ones that you can obtain as varieties of tropical ideals? Those I want to call matrices that are tropically realized. And you should think of this as kind of generalizing the notion of linearly realizable. Linearly realizable is saying this thing, but for saying you can find a classical ideal where the variety of that classical ideal is the linear space of the matrix. And here we want to say the same thing, but maybe it's a bigger class. So from the definition, it follows that linearly realizable matrices are tropically realizable matrices. If you have a matrix that is realized by a subspace, just take the ideal that defines that subspace, and then the variety of that ideal, of the tropicalization of that ideal, is going to be the tropicalization of the subspace, which is the point of the matrix. So this is some class of matrix that includes all realizable matrices, and yeah, wondered if maybe is this all matrix? Can all matrices be tropically realized? So then in 2019 with Jan Drijsma, we realized, okay, yeah, actually no, this is not all matrix. And we showed that the Vamos matrix direct sum uniform 2, 3, rank 2 on 3 elements cannot be tropically realized. Let me tell you a little bit about this, the idea for this proof, because it's quite interesting. It's actually related to matrix products. And I don't know how many of you, I don't know if you're familiar with that, but for instance, let me tell you what a tensor product of matrices is. So suppose you have M a matrix on M elements, and N a matrix on N elements. Then a tensor product of the two matrices is a matrix on the product of the ground sets. So think of it as the ground set is now a rectangle. Here is M and here's N, and the ground set of the matrix of the product is going to be the rectangle, such that all the rows are, when you restrict to any row in this rectangle, you get the matrix M. When you restrict to every column in this rectangle, you get the matrix N. But the rank of the full matrix needs to be the product of the ranks. If it's loopless, then yeah, for this to be right, I need loopless, because otherwise in some columns you just want to have all loops. Yeah, so for this to be exactly right, as I said here, you want loopless, otherwise, but this notion makes sense for a loop matrix, just it's not exactly this. But yeah, so a tensor product of matrix is a matrix of the product of the ground sets, where the columns are the first matrix, the rows are the second matrix, but the rank is big. The rank is the product of the ranks. You can prove that anything that satisfies these two properties has to have rank at most this. That's not hard to see. But tensor product is when it has rank exactly. And actually, this is a concept that was studied by matrix theorists from the 80s, I think, already. They were interested in, okay, do matrices always admit a tensor product? This was a question that they cared about in the 80s. If I have any two matrices, can I always construct a tensor product of the matrix? And that was finally settled by Las Vernias in the 80s or 90s, where he showed an example that these two, Vamos and View 2-3, do not admit a tensor product. And that's really the reason why this is not tropically realizable. So let me show you why that is. So why is it that the Vamos matrix times U23 is not tropically realizable? Well, assume it was. Assume you had a tropical ideal, one of these sequence of matrices that where the variety is the Bergman fan of Vamos matrix times U23. Well, this is a matrix on 11 elements, right? 8 plus 3. So it would be to be an ideal on 11 variables. And the fact that the variety gives you the Bergman fan with multiplicities once on the maximal counts. So that's part of what I'm assuming here, that the multiplicities have to be 1. Then that means you can show that really means that in degree 1, you have to put, so what's the matrix that you put on the monomials of degree 1, on the 11 monomials of degree 1, on the 11 variables? It really needs to be the Vamos matrix times V. So basically, like you have 8 x variables and 3 y variables. And on the x variables, the polynomials that you have are the circuits or the unions of circuits of the Vamos matrix. On the y variables, you have the circuits of U23. That's what happens in degree 1. But then you have all these matrices sitting on top of that. And you should have a matrix of degree 2, a matrix on the monomials of degree 2, degree 3, and so on. Well, let's think about what the matrix on the monomials of degree 2, what it would have to be. Well, it would have to contain all the circuits that you have in degree 1 times x, for instance, or all the circuits that you have in degree 1 times y. So if you look at the matrix in degree 2 restricted to the monomials, the mixed monomials that come from a variable in the x variable, like in the Vamos matrix times a variable with the U23, this is one of these products of matrix. Like if you restrict to so there are 24 of these monomials because there's 8 x variables and 3 y variables. And if you restrict to the rows of those 24, you should get the Vamos matrix. by this compatibility condition. If you restrict to the columns, you should get the U to 3 matrix. So it's one of these products, but it also should have this rank product of the ranks. The rank of this matrix on these 24 monomials should have rank 8. And that's because if you had smaller rank than that, then the Hilbert function of your tropical ideal would not be the, it would not be the Hilbert function that you expect for something of degree 1. So by thinking about Hilbert functions, you realize that this matrix has to be a tensor product of the Vamos matrix and U to 3. And then we use this result of Latvernius that showed that these two matrices don't have a tensor.
I thought in this compatibility question, it's only requires to be a quotient.
That's right. But if you assume that the ideal is saturated, so that you can saturate the ideal, like tropical ideals are close to their saturation by variables. If you saturate the ideal, you can assume that. Yeah. So for instance, I was already assuming that here because in degree 1, it could be that you start with, so if you truncate your ideal and remove everything of low degree, you could still get the same variety. But if you saturate, you recover things in low degree, and that I was kind of assuming that here. So yeah, you're absolutely right. This is just like the sketch of the proof. Anyway, my point with going into this level of detail is to show you that realizability of burn and spans of matrix are related to matrix products, and really, for instance, the fact that this one is not tropically realizable boils down to the fact that there is no tensor product between these. And I would love to understand products. There's tensor products of matrix or symmetric products of matrix, which is a very related notion that is also very connected to tropical ideals. I would like to understand them better, and I think basically this result of Latvernius killed the field in the 80s, and no one thought about that anymore. And now I would like to know more about it. Yeah.
Are these the only cases where you have something that is not tropically realizable?
Yeah, so this audience is great. Yeah. I think it's the next thing I have over here. One more thing you can prove about this is not hard to see, is that this collection of this class of matrices, the tropically realizable matrices, are closed on their minors. Okay, so they're closed on their deletions and contractions, and that's because, I guess, deletion of a matrix. If a matrix is the Bergman fan of the matrix is a variety of an ideal, then the Bergman fan of the deletion is maybe take the ideal and intersect it with a smaller polynomial rate. Like just ignore everything that has some of the variables, that's deletion. And contraction is maybe setting some of the variables equal to infinity. Like in every subset, delete the monomials that use that variable. That preserves being a tropical ideal and gives you deletion and contraction. But then, of course, then the question is, what are the forbidden minors for this class of matrices? So my student, Nick Anderson, in his thesis, showed that there's infinitely many forbidden minors. And the way he did it is, he realized that this argument of Latvernius, showing that there is no tensor product between these two matrices, generalizes to kind of an infinite family of matrices that look like the Vamos matrix times U to 3. So yeah, so there's an infinite family of matrices. This is like the Vamos matrix 1, but there's Vamos matrix number 2, Vamos matrix number 3, and they grow in size. And for all of those, they don't have tensor product with U to 3. So all of those, the matrix obtained by those matrices times U to 3 are non-realizable, and they don't have any common minors that are not tropically realizable. So you can show, kind of generalizing this argument, that there's infinitely many forbidden minors.
How about duals?
How about
Duals.
I don't know. Yeah, this duality doesn't seem to be so nicely behaved with respect to. I don't know what to think at this point. I think if you ask me today, what I would say is that maybe I think tropically realizable matrices are much closer to realizable matrices. They might even be the same. We don't know an example of a matrix that is not realizable, but yes, tropically realizable. I don't know an example of that.
I mean, the sum of things, direct sum of things that are realizable, but in incompatible characteristics, right?
I wouldn't know how to make a tropical ideal that in degree 1, I know you can put that, but in degree 2, you would have to create some kind of tensor product of the two, and creating tensor product of matrices that are realizable for different fields is not, might not exist. I don't know. A very concrete problem that I think we are at the stage of attacking now, even computationally, is the Vamos matrix tropically realized. So let me tell you, my intuition today, my guess today would be that it's not. And one way you could prove that it's not is, well, suppose you have an ideal where the Bergman function of the Vamos matrix is the variety. That means in degree 1, you have 8 variables, 8 monomials of degree 1. You would have to put the matrix. The matrix you have in degree 1 is the Vamos matrix. But then think about the matrix in degree 2. The matrix in degree 2 is a matrix on how many monomials are there of degree 2 on 8 variables? 36, if I remember correctly, 36 monomials. So it's a matrix on a ground space of size 36. You can predict the rank. The rank comes from the Hilbert function that you would expect it to have, which I think takes 10, something like that, 10, maybe 10. So it's a rank 10 matrix on 36 elements. And you already have lots of circuits that it would have to have. Like every time you take a circuit in degree 1 and you multiply it by a variable, that should be a circuit in this matrix of degree 2. And the idea would be to prove that that matrix doesn't exist. There is no way of creating a matrix on those 36 elements of rank 10, having that specified collection of circuits. And of course, you need to have more because they don't satisfy the elimination. But so you cannot do it brute force. You need to, it's big enough, 36 elements, rank 10. You need to be clever about it. But yeah, maybe this can be done even computationally to show that you cannot have something on the grid. All right. I had a slide here about something we've been doing more recently, but maybe I won't go into full detail of that. I'll just tell you the theorem that something else we've been thinking about is a Nullstellensatz for tropical ideals. So the classical Nullstellensatz for ideals in a polynomial ring says that if you have an ideal, and it turns out that the variety of that ideal is contained in the variety of one single polynomial, so S is just one subset here of one single polynomial. Let me tell you the classical version. Then some power of that polynomial is in the ideal, right? Over an algebraically closed field, I guess. So what would be the analog? The tropical analog of that is that if you take a tropical ideal and the variety turns out to be contained in the variety of one single subset of lattice points, like one of these things, then that's because some power, and then by power I really mean like take S plus S plus S, so these lattice points plus like Minkowski sum M times from that set with itself, then that lands inside your tropical ideal. In some high degree, you have this subset there. We cannot prove that, but we can prove it if the ideal is realizable. But in general, what we need to do is take the saturation. And what I mean by saturation is this is a collection of lattice points. And then just like take the convex hull and take all the lattice points that lie inside the convex hull. Yeah, so it turns out that when you think about these questions, of course, there's a lot of arithmetic of lattice points happening because, yeah, S plus S plus S, like you might not fill all the, if your subset lives in a proper sublattice of the lattice, then you never get filled the whole thing. So you need to saturate. And we deal into these, we have to deal with these kinds of issues. Yeah, there are some particular instances of these that are interesting. So what happens, for example, if the variety of the ideal is empty? If you apply that to this, it says that your ideal actually contains a singleton. So if all the conditions for your variety are incompatible, there is no direction that satisfies that for every subset the maximum is attained twice, then that's because there is a single subset that certifies that, which is that it contains a singleton, one lattice point alone, and that one certifies that no direction. That's the minimum. So this is, yeah. Or things like, maybe let me just skip this. It is saying that zero-dimensional ideals have arbitrary Newton polytopes inside them. As a consequence of this, you can get. Or this was just a remark on this, how this question relates to the integer decomposition property of polytopes. That it's not just that a polytope is a summand of another polytope, but it's really that every lattice point here can be written as a lattice point here plus a lattice point of the other one. You can ask me later if you want to know that. But let me just finish with many things that we don't know and that I would really like to know. I chose like two things that I'm particularly curious about. And one of them is, how can these tropical ideals be finitely described? Okay, so the way we define them is there are an infinite sequence of matrices how can we like finally describe this infinite sequence matrix? How do I email you a tropical ideal? Turns out it's not so, it might not be possible. It's not possible because we have this paper with my student Nick, where we prove that actually already in one variable, there's uncountably many tropical ideals. And that means that tropical ideals have no chance of being finitely determined, if not finally generated, but in any way that you want to describe it with just finitely many information, you would only be able to capture countably many of those. And there are uncountably many, so you cannot expect all tropical ideals to be finitely described, right? But it's the same with real numbers, like real numbers are uncountable, they cannot be finally determined, and still I email you real numbers all the time. So the hope is that some tropical ideals can be finally, what are the rational numbers inside, or the algebraic numbers inside the tropical ideals? What I would really like is, so how do I tell you, okay, the matrix degree 1 is this, degree 2 is this, degree up to 7, and then from there on, continue in some way. I don't know how to say, and from there on, continue in some way.
So sorry, because there is no notion of the minimal, right? I mean, if you give me
There is no notion of what, sorry?
of minimal family containing something up.
They're not close on their intersection. This is a big problem. And this is related to what I'm saying. This is amazing. Yeah. So this is really related to the question of, we don't have enough commutative algebra tools. I feel that we don't have enough commutative algebra tools to tackle these questions because they're not close on their naive sum of ideals. They're not close on their intersections. We don't really know what a prime ideal is. So if there was some way of coming up with these things that would make things easier, primarily propositions. Sorry?
Product of ideals.
Product of ideals, for instance, they're not close on their products. What would the product do? And a very concrete question is, I would like some notion of like ideal generated by some subsets, right? So if I give you k many subsets of lattice points, how can we define the ideal generated by those? Or how can we construct a tropical ideal that we could call this? And maybe what I would like this to satisfy is that the variety is maybe the stable intersection of the varieties of each of these. Right? We know how to do it for one subset, which is a paper of Alex and Jeff and Noah Giansiracusa. They constructed what the ideal generated by one subset is, and this has to do with transversal matrix. So in every matrix, you put some transversal matrix. In every degree, you put some transversal matrix arising from the subset S, but we don't know how to do it for more than one subset. So this is really something that'd be very useful. And then another question, maybe the philosophy that I'm trying to communicate here is what geometric information of a variety, of a classical algebraic variety, is captured by the tropical ideal that you get when you tropicalize the variety. So I think, for instance, in tropical geometry, often it happens that you have some problem that you want to study classically, you tropicalize it, and you check if the information that you cared about was captured by the tropical varieties. It makes sense to attack the problem tropically because you can still recover the information from the tropical varieties. And that happens sometimes, like when you do intersection theory, for instance, in the plane, but not all the time, right? And so, for instance, examples that come to mind are duals of plane curves. If you take a curve and you tropicalize it, the tropicalization of the curve does not determine the tropicalization of the dual curve in the plane. But now we have another tool. Well, maybe it does if you tropicalize in this sense. If you look at the tropical ideal, which is strictly more information than the tropical variety, maybe that's enough to recover the dual curve. Or there are these papers on like bitangents of particle curves where it doesn't always, you don't always get the right number of curves. What if instead of looking at the tropicalization as a variety, as a curve, as tropical curve, look at it as a tropical ideal? Maybe this contains enough information to tell you, okay, you're in this case by tangents, or in this case, and you can expect. I don't. This is more of a philosophy than a really concrete problem. But look for situations where the tropical variety maybe did not capture all the information you wanted about the algebraic variety, but maybe the tropical ideal does. And then, related to that, maybe the last thing I'll say is something I really haven't thought much about, which is this compatibility conditional matrix that form the tower. how do matrix invariants behave in this tower? So for instance, the rank, we said the rank of the matrix has to be controlled by a polynomial, eventually a polynomial. But what about other matrix invariants? What about the beta invariants of the matrix? What about the top polynomial? What about all the matrix invariants that we like? Are they restricted by coming from a tropical ideal, by looking at the tower? What can we say about the asymptotic growth of these matrix invariants? Maybe that tells you some information about the algebraic variety that you have in the back. Yeah, I'll stop it.
Maybe
You already started talking, so.
sorry. Is there any, I presume there's some abstraction in making a Hilbert scheme.
I mean, you could make the definition of the Hilbert scheme, yeah. You're living inside some infinite product of Grassmannians, and but I think it's hard to study it. Yeah, I think the definition exists, and I think some people have thought about that, but I'm not sure how much you can say about it. Like trying to understand the realizable locus versus the whole, like living inside the whole thing. I haven't thought about it myself, but I know the definition can be made. I don't know how much you can say about it, but that's right. Yeah, that's a natural question. Yes.
Can I ask one other question before judging?
Yes, yes.
What about the non-constant coefficient case? Is there?
Absolutely, yeah. So actually, all the papers are written in the non-constant coefficient case. Here, for the sake of focusing on just matrix and not valuated matrix, I kind of remove the coefficients, and it makes it easier to understand. But yeah, you can see all the non-constant coefficient case there.
Yes. Can you say more about how you initially generate a tropical ideal? Like, how do you define it? And depending on this answer,
yeah. So for instance, you fix a weight vector, and you have a subset living inside your ideal, then the initial term of that subset is just take all the lattice points where the maximum dot product with your weight vector is attained. Like for instance, if this is your weight vector, then the initial term of these 5 points is just going to be these 2, because that's where the maximum is attained. And you do that for all the polynomials in your ideal, for all the subsets in your ideal, and you get another tropical ideal, which is the initial term, the initial ideal. Yeah.
does this mean you can tropicalize a tropical ideal?
Tropicalize a tropical ideal.
You can define tropical. I don't know so much about this, but like you can define tropicalization with Hilbert degeneration.
Sounds like what you're doing is saying how to recover the variety from the ideal.
But that's what he said about like putting the weights.
Yes.
He likes the balanced plan.
I see what you're saying, yeah.
Okay.
So you can define the variety in that way. The variety associated to a tropical ideal, for instance, is the collection of all weights that give you the generations that don't contain monomials, something like this. And you can go further to define multiplicities on these.
I see.
So you can study it from this point of view. You're absolutely right.
Okay,
Yeah.
okay.
You can study the variety. Yeah.
So Dave, at the AIM week in 2017, some of us worked out the Hilbert scheme of the double point on the line. And it's like some infinitely branchy Berkovich looking tree.
Okay.
But idea about like the representability, have you looked at there are these matrices that are representative over skew fields, but not over fields. And I wonder if that's enough algebraic structure to produce an ideal out of it.
I haven't, yeah. I focused on fields all the time for working. But you're right that it makes sense to look at more general objects.
Non-Pappus.
Non-Pappus, or is that, no, isn't it non-Desargues or is it non-Pappus?
Non-Pappus.
Okay.
Is there a classical problem that you can solve by considering the Tau rescue?
No, I mean, this is partly, I think, to be honest, this is partly why this has not like taken, like, yeah, been more popular yet. It's because I don't have an application like of a problem that is solved by this theory that cannot be solved in any other way. I would love, so that's kind of what I mean here. Maybe some problems where just looking at the variety was not enough, but maybe looking at the ideal itself, which is more at the scheme, it's more information that allows you to tackle the problem. I haven't myself found one, but I would love to if you guys have
What
any.
about the solved problem? Doesn't have to be an unsolved problem, like a solved problem.
Yeah, I mean, anything you can do with varieties, you can do with schemes as well, because the scheme is more information, but yeah, I haven't. Yeah.
This middle question feels a little bit optimistic. Like, what's the expected answer if I take my S's to be like circuits of the Thomas matrix?
So that's why I mean that maybe it should be the stable intersection of the.
I don't know. Do we expect, is the existence of such a thing?
No, so if you take the circuits of the Walsh matrix, each circuit would cut down the dimension by 1, because we're taking stable intersection and not intersection. So you would not expect the Bergman fan of the Walsh matrix, but something of much smaller dimension, because as many as circuits you put in there, the codimension would be the number of circuits.
Should these be complete intersections? That you think of this?
Exactly. So this should be like only for doing the case for of complete intersections. You put all the circuits, that wouldn't be a complete intersection.
Well, so this gives you like a definition, yeah? I can put like random polynomials where SI is the Newton polytope, and I could just take a realizable thing associated to that ideal.
But then you need to put them all together into one ideal.
Yes, I generate ideal with polynomials that have this support. That's a complete intersection. Maybe it's very small.
Yeah. Yeah, I guess the question would be to understand combinatorially what it is that you get there.
So the thing with transversal matroids that Jeff and Noah and I do, if you put in the trinomial, the linear trinomial, you get the non-realizable guy, right? That's the combinatorially easier guy.
Yeah, that's
The
right.
tropicalization has harder combinatorics than that guy.
Yeah, like Sin2 of a generic representation of the uniform matroid is like extremely complicated.
Yes, in some sense, the non-realizable ones are easier combinatorially than the realizable ones. And this construction for one subset is not realizable. It's not the one that you're saying. So. Boom, great. Thank you so much for all the